Okay, so in this video, we're going to be calculating the required nominal moment, and also we're going to be doing the uh, plastics modulus. So this is numbers 3 and 4. So I'll go back to my notebook here, and you can see I wrote at the top 3.2.6 beam design dash interior. And then I put three parentheses, calculate the required nominal moment. And I wrote here that Mn is equal to nominal moment, Ma is actual moment, and then this Greek symbol, and that's just the name of it's just slipped out of my mind, is what's referred to as the safety factor. So I want you to take a moment and actually write these things down. So you have them, and the formula that we're going to use here is going to be the nominal moment. So M sub n is going to be equal to the actual moment, A, times the safety factor. So Mn is equal to the actual moment, and the actual moment is right here on our chart. It's 40,500. So I'm going to put that in. So 40,500, and then that gets multiplied times the safety factor, and the safety factor is a given number. It's 1.67. So if we get the calculator out, and we take 40,500 times 1.67, we're going to get 67,635 pound-feet. I think it is. Yeah, 67,635 foot-pounds. Okay? So, because this is foot pounds here. I forgot to do the units. So, that's for calculating the nominal moment. Now, the fourth step here is to determine the required plastic section modulus and to select an efficient wide flange beam. I should write beam there. So I'm going to want you to write all this stuff down. Zx is going to be plastic section modulus. The M sub n is the nominal moment that we just calculated right up here. And then the Fy, that is the yield point of steel. And by the way, that's a constant number. It's given to us. We don't have to calculate it. So here is the formula we're going to use to do this calculation. It's Z sub x is greater than or equal to the nominal moment divided by the yield point of steel. So I'm going to take and start to fill in this little problem. So my Zx has to be greater than or equal to the yield, sorry, not the yield point, the nominal moment, which is 67,635 foot-pounds. 67,635 foot-pounds. And that's going to be divided by the yield point of steel, which is 50,000. And that is in pounds per inch cubed. And we want our answer to be in pounds per, or in inches cubed here. So we've got a little bit of a dilemma, because up here we have foot and down here we have inches. So we're going to have to convert these feet into inches, and you do that by multiplying 12 inches over 1 foot, and our feet are going to cancel out. Our pounds cancel out down here, and we can do the math now, I think. So I've got my 67,635. I'm going to multiply that times 12. That equals that number. And then I'm going to divide it by 50,000. Divide it by 50,000 equals 16.23. 16.23, and that is going to be inches cubed. Okay, now next thing is we need to select an efficient wide flange beam. So that comes from this website right here. The link for this is right on the front of the page. You should be able to download this document from my student share folder, and you'll go to this web page, and what you're going to do is you're going to go to where it says steel sections first, and then you're going to look at wide flange beams, and then you're going to hit properties. Now where we're going to be looking is we're going to be looking in this column right here, ZX, and what we're looking for is a number, whoops, I got to get back to that, that is close to and over 16.23. So that's the goal here, is this column we want to be close to and over 16.23. Now you can see this column starts out pretty big, and this is a W44 by 335. Now the W44, that refers to the height of the beam. This beam is 44 inches tall by 335, and the 335 is the weight of the beam per foot. So that's what they got right here, nominal weight per foot. So this beam is 44 inches tall, nearly 4 feet, and it weighs 355 pounds per foot. You want the lightest beam that you can possibly find that is going to meet the criteria also of being close to this ZX number. So I'm going to save you a lot of problems here, and I'm just going to pull this down right down to the bottom because I've done this. And what I'm looking for here is this number again in this column, and you can see we've got 17.4, which is pretty close to 16.23, and that's about, frankly, above this the numbers are all very large. You'll also notice that there is another one down here that could work. It's 18.7, and that's a W10 by 17, but the thing is, this one weighs 17 pounds per linear foot, and the W12, let me find him again, times 14 weighs 14 pounds. So this is our lightest beam, and we want to use the lightest beam we possibly can. So I'm just going to leave that one highlighted. So back on my sheet here, I'm going to write this beam's name down here, and this is going to be a whoops, I gotta make sure I get this right. W12 by 14. So you can see I wrote that down there, W12 by 14 beam. Okay, next thing we're going to be doing is we're going to be starting to do the shear strength, and then we'll get to deflection limits and actual deflections and selecting the final design.